More bubbles.
Cover yourself above.
Okay, on the count of 3, show me your board. 1, 2, 3.
Got stuck.
Very good. It is exothermic. Well, have fun. So with this idea, everybody, and as we jump in, Allie, did I hit press play? Yes. Last time we learned about calculating. So this first sentence was actually the same I can or objective we had last time. I just changed the second part. I removed our check marks other than last period. Okay, so last time we learned how to calculate an enthalpy change for a reaction, which represents the actual value of the joules or the kilojoules of heat that either comes out when it's exothermic or went in when it's endothermic. Okay, with this demo, we could theoretically do that experimentally. We'd have to change a few factors because it's not a very controlled setting. What are the pieces of data I need to calculate the heat of a reaction? Like, what are the values I'd have to gather from a lab setting? Anyone by raising a hand have an idea of one set? Yeah, Bryson.
Specific heat?
Good, so one, we would need to know the specific heat of the things reacting to know how much it changes. Often in our problems we use water. In this case, it wasn't in water. We'd probably do the specific heat of air, right? Because that was like most of us around by. Good, have a smiley face for that. What other pieces of data do I need? Okay,
Mass.
good, I would need to know the mass. Have a smiley face, right? So I need to know how much gas did I actually use, as well as how much oxygen gas did I also use. So we'd want to do it in a much more controlled setting where I put in the methane, I put in the oxygen, so I knew how much I had, right? So we need mass, we need specific heat. Who has my final data piece? Bryson? The change in temperature, right? So we'd have to know how much temperature change it went up. Now in this case, using a normal calorimeter would not work because our styrofoam cup would melt if we try to do this reaction in there. And so that's where you have a more complicated things. Often you can use like a metal. They have some metal calorimeters. They sometimes call them bomb calorimeters when they're designed to contain explosions. But in a sense, you can do it inside of it. It can actually measure the temperature change for you, and then you could calculate Q, and from there we could then calculate delta H. Our objective today is to still calculate delta H, but through different means. So we're going to learn 3 different ways to calculate delta H today, and it really all depends on what's given. So my phrase of the day that I'm going to use are pay attention to context clues. Depending on what the problem gives you will help you know which method to use to solve for it. Okay? All right, let's take a look here. Before we get into how to find delta H, we're going to look at one way in which delta H can be used. Oh, side note, by the way, for you guys we had a little bit more time, but with B6, I didn't have enough time last period to go over that practice problem that we did right at the end for them. So I made a separate video walking through that practice problem. So if you are a little confused from last time's lesson, there's just an extra little video on Canvas that you can go back and watch if that would help too. And then also just a reminder too that there are also all the AP classroom videos, right, on every single topic. So if there is ever a topic that you're like, I just don't quite understand this all the way, or maybe I just need a refresher because it's been a while, just a reminder that those are available to help you as well. Okay? All right, we've seen these graphs before with phase changes, but let's connect it to this unit. Well, that's why I feel weird. I didn't put my watch back on.
Yeah.
I was like, something was missing in my life. My best friend. Okay, we're better now. Okay, so with a phase diagram, right? So keep in mind your axes. So this is temperature. What does temperature measure when we talk about chemicals?
Movement.
The movement, right? So if temperature is going up, they're moving faster. Okay? So right here we're starting with an ice cube. Okay, which is a solid. Okay? So imagine right now we are an ice cube, because we're kind of like an ice cube because you're not really moving. You're all moving slightly, so you're vibrating, right? But you're not really moving in your tables. Okay, so if I start heating up the room and we were an ice cube, what are the molecules going to start doing? Start moving a bit, right? Not true separation yet, but you're not as latched to each other as you are as a solid, right? So we move up here, we get faster and faster. We get to a point where you guys can't move. But notice, heat energy is still being put in. idea. So heat's going in. I'm still heating my ice cube. But the molecules aren't actually moving any faster. Zach?
The heat is going to start to break the bonds in the NX.
Very good, right? So we get this idea of the constant because we're breaking bonds. Remember, breaking bonds or IMFs takes energy, right? So the process of actually melting, meaning the phase change, so going from the solid to the liquid, or if you're looking at reverse, the same holds true, the temperature does not change, right? If you have a pot of water on your stove and we were at sea level, right, or I guess an ice cube, let's start with an ice cube, and we're heating it up, right, that ice will not go past 0 degrees Celsius until it's all melted. It's going to stay at 0 until everybody is a liquid. Then we can start making the liquid move faster. Okay, so the liquid moves faster. So now this would be you guys are standing up. You're still kind of close by each other, but like you can move around freely, right? Okay, until the next phase change, right? So the point at which we are trying to boil it or condense it, condensation. Once again, the boiling water at sea level cannot go above 100 degrees, right? Your pot of water on your stove, you cannot get above 100 at normal pressure. It's going to stay at 100 until, since it all evaporates into our gas phase. Now, technically, if you capture the gas, you can make the gas get hotter and hotter and hotter, right? So this would be the point where you guys would be bouncing around the walls and the ceiling and everywhere, right? There'd be a lot of pressure going on here, okay? But there's this idea of that plateau because of the energy needed to break the bonds, okay? Now, connecting it to this unit, we all learned that before in our IMF, but connecting to this unit is there's an actual delta H value for the phase change. For freezing and melting, it's known as the delta H of fusion. I don't like that word choice, but that's just what it is. Okay, the delta H of fusion tells you the exact energy it takes to phase change the substance, which would vary if it was water or something different. And then this one is the delta H of vaporization, which I do like. That one makes more sense to me. And then I'll show you how we're going to use these mathematically on the problems right below it. Okay, everybody okay here? Okay, so let's take a look at a problem. So the cool thing is with delta H is delta H, right, is always a relationship of joules to a measurement. Often it's joules to moles or kilojoules to mole, but it could be to gram, just depending on how it's measured. But because it is, if you want to label it, this is a 2-unit relationship, you can use it stoichiometrically. So it's a great way to convert between grams to joules or joules to grams, or with moles or whatever unit you're given. So let's do the first one together, and then I'll have you try one for a smiley face. Okay, so our problem here says calculate the energy needed to vaporize. Now, key point here, what type of phase change are we going through? Because there's 2 different units that could be, okay? So we're using the vaporization one. So this is the one we want to use, okay? So it's telling me I have 15 grams of H2O. The relationship is that for the vaporization of water, it's 2,330 joules for every gram of water. And so by just timesing it out, we can calculate how much heat do I need if I want to vaporize 15 grams. All right, if I'm trying to heat that much up, what do I need? And I got, where's my answer? I remember. A big number. That's what I remember. Someone had it before I tied my page.
34,500.
Thanks, Bryson. That was my face probably on.
Also, oh wait, no, sorry.
Oh. Did you type something in wrong?
I typed 2,300, that's my bad.
Oh.
34,950.
Thank you. represents I would need that many joules of energy to go from my liquid to a gas. So, questions on how that one works? Yeah, Jack?
Is it just 1 gram on the bottom?
Yep, it's just per 1 gram. Yep. I think you should have clarified that. Now keep in mind that just like all our conversions, if I was starting in joules, we could still use this, it would just flip. Okay, so just like all our conversions can be gram over mole or mole over gram, this one can be the same as well. Okay? Alright, I'll do B with you and then we'll try C with your table buddy. Excuse me. So this one, key thing, once again, notice the units. We do have to make sure the units work out. So since I'm in a kilojoule, I do need to do a little pre-step, I guess you could say, and get it into, sorry, I said kilojoule, I meant kilogram. Sorry, people. Kilogram, so I do need to do a pre-step and get it into grams first. So there's 1,000, no. Sheesh, people.
5,700.
There's 1 kilogram in every 1,000 grams, or just move the decimal over 3, however you like to think of it. Now, since I'm in gram, now I can use my same relationship that 1 gram is 230 joules. So sometimes, as always, you have to maybe convert some units first, but it should work out either way. So I got 1.34 times 10 to the 7. I put it in scientific notation just because there was a lot of zeros. Questions on that? Okay, turn to your table buddy, use their name and say, hey, let's do part C together. Emily? Or whatever her name is.
Let's do it.
When you're done, set your pencil down so you know you're finished. And then maybe find out with your table buddy what's something you have in common with each other.
Oh, what did you get?
Ask them how many siblings do you have.
Already.
When's your birthday? We're born in the same month.
Okay, we can do that. With these classes, I never know. I took earth science.
Has everybody had a chance to solve? I give you another minute before we check our answer. Okay, if you got an answer of 1.63 times 10 to the 5th, You can have a smoothie. Huh?
You got
What? 1.63 times 10 to the fifth?
Oh, yeah, that's the same.
Okay, questions on these types of problems? Okay, this is what, so homework 6.5, we'll be having a practice problem with this. Once again, in our word of the day of context clues, if a problem on the AP exam gives you H's of vaporization or H's of fusion, then you're most likely going to probably use this stoichiometry somehow. Now, keep in mind, this heat just represents if it's already hot enough. So it doesn't take into account like the energy needed to get up the slope. Right? It's saying once I get up the slope to cross the plateau, that's how much energy I need. So I actually saw there's been some problems, and I think we have one on our lab next time that we'll practice, where you actually have to do, in a sense, 2 steps. You first have to figure out, okay, how much energy is needed to get to the temperature of 100, and then how much heat do I need to vaporize it. So keep that in mind that this energy is only the energy needed if this is already at 100 degrees. Okay? All right, so now we're going to get into our different ways to calculate our delta H. I can't remember whose voice I heard. So if you're brave, I heard during when you guys were talking about whether it's endo or exothermic, I heard someone mention about the idea of heat in versus heat out. Is anyone brave enough to say it was them? So in my demo, did I put heat in? Yeah, right? That was the whole point of Brissa, right? Brissa put the heat in. So how do you know that it's exothermic? Jack? Yeah, there was way more heat out than the kickstart that went in, right? So with all of our reactions, besides very, very simple ones that are just a single formation or a single breakage, most reactions have some energy in and some energy out, right? And relating it to the bonds, we know it takes energy to break it. This, by the way, isn't in your notes if you're looking for it. Sorry. It was just a thought I had when I was reviewing my lesson to maybe help. So, but the idea is it takes energy to break bonds, and then energy gets released when they're formed. So another way you can calculate delta H is if you actually knew the cost of bonds. If you knew how much it took to break a single bond of carbon to carbon or hydrogen to oxygen, and can compare it to the energy of them forming, you can calculate delta H that way. And scientists have calculated all those numbers for us. So there are giant data tables that will tell you the bond energies. And so if you're given one of those tables, the way you can find delta H is by saying, all right, let's sum up the bonds broken and minus the bonds formed. Oh, by the way, I don't think we've seen this symbol before. This right here, for those that haven't learned, that's the Greek symbol called sigma. It means to sum, so it just means to add everything up. So we're going to add up all the bonds broken minus all the bonds formed. So that's what that fancy symbol means. We actually see it a few times today and then actually throughout the year. But just like how delta always means change, this always means sum. And that's not specific to chemistry. So, okay, let's take a look at the problem. Okay, so our problem here says, what is the value of the enthalpy change for the reaction below based on the bond enthalpies? Once again, context clues. Okay, so our context clues is they give us bond enthalpies, and so we're going to use the equation we just saw. Oh, side note, that equation is not on your formula sheet. If you want to make note of that, hopefully it's a simple one because it's just bonds broken minus bonds formed, but it isn't on our formula sheet. Yeah.
Do we put anything in the parentheses?
No, because we used to, and then I found it confused students last year, so we're not going to put anything in there. I was going to get rid of them, and I forgot to. So just leave them blank. Sorry for that bug too. Good question though, Ian. Yeah.
For the AP test, do you have a list of all the formulas that aren't on there so we can like?
Yeah, so when we do our review month, I'll go over, there's only like 4, maybe 5, depending on if you like that one or not. And so yeah, I'll go over so you can kind of like focus on making sure you remember those. Good question.
Thanks.
Okay, so the idea is, once again, we need to do bonds broken minus bonds formed. Well, I know it's 2 carbon monoxide, CO, but if I look at my data table here, we have a carbon to O double bond and a carbon to O triple bond. So the first thing you have to do if this is the method that's given is you have to draw Lewis structures. Okay, so the first step is we have to draw Lewis structures. Because we need to know, is it a double bond breaking, or is it a triple bond breaking, or a single bond between them? Okay? I'm going to go through the Lewis structures a little like fast and drawing them because that's not the objective right now. I want you to focus on like big picture. If it makes you feel better, I've actually seen some questions where they draw the Lewis structures for you already, because that speeds up the question a lot. But if you need help reviewing Lewis structures, come see me and I'd be happy to like remind you how to do it. Okay? So the Lewis structure for carbon monoxide, CO, is a C triple bonded to O, like this. Now, I am going to draw the ratio in the equation. So I'm going to draw 2 of those same molecules because of the 2 up here. Okay, it's reacting with oxygen, which is a double bond with itself. And it's turning into 2 carbon dioxides. So carbon dioxide is O double bonded to C. Technically the dots don't really matter, but in drawing your Lewis structure you would normally have them there. And then I'm going to draw 2 of those as well because of the 2 in the balanced equation. So pretty much we're just changing the equation they gave us into the visual of what bonds are present. You opened that so creepy. So sorry. I like went to the door and I was like, yeah. Yeah, I thought I did, so I said it. I don't know if I did though. I just thought I did. Okay, everyone have this drawn? Everyone good there? Okay, I'm going to use 2 different colored markers on purpose, so if you also want to use your highlighters to differentiate here. What's our equation we need to do? What minus what? What costs money? To break bonds or form bonds? Break bonds. So we got to do bonds broken. And then we got to minus the formed. Right? So we're taking into account, okay, we have to pay this much to break the bonds, and then it's going to give us back this much, so what's our overall energy difference? Okay? Now looking at a balanced equation, the ones that are going to be broken are the reactants, because the reactants are the ones changing. So I need to break these 2 bonds and this bond. So a C to O triple bond costs me how much to break?
1072.
1072, and I have 2 of those that I'm breaking. So if you want to draw an arrow, this came from, right, our data table. All right, I'm going to add, so that takes care of these 2, plus how much does an O double bond take? Is that 498? Is that what that says? Okay, so everything in red are the cost of breaking my bonds. Then I'm going to subtract it from the ones that are being formed. So I have 1, 2, 3, 4 C to O double bond, which is 799. So minus 4 times 799. So I'm paying this much, it's going to pay me that much. What's our difference? Questions on my setup? When I plugged that into my calculator, I got negative 554. Yeah, Jack.
On the work for this, are they gonna have all of like the bond types and bond equities for you?
Yeah, so this is something that like has to be given. Now I will clarify this for the homework. So the homework that goes along with this is 6.8. I put slash because it's like one side is 6.8, one side is 6.9. Your homework, it's not on the paper. Because last year we had textbooks, and so they just looked them up in the textbook. And I didn't realize that until like this morning. I was like, oh no, they don't have the data tables. So I'm gonna post them on Canvas, the data that you need. So do this right now really quick, everybody. Find your homework. On the top of 6.8, put a little star and just say, look on Canvas for data. Because otherwise you're gonna go to it and you'll get very confused on how to solve it. Thank you for asking that, Jack. But yeah, like on the AP test, they don't give you data, like tables of data. It would just be within the problem like this one. So, any other questions on this question? So once again, 6.8 on the top of it, just little star, say, look on Canvas for data tables. Okay, I have a question for you. What's my unit? It equals delta H, so that's not a bad thing to think of. So delta H is what it equals, but it's negative 554. There we go, yep, because it's delta H, and delta H is kilojoules per mole. You could also think of as, those are what the values, I just didn't put them in for simplicity, but all of our bond energies were in kilojoules per mole. Okay, whisper to your new friend at your table, is this endo or exothermic? Whisper to them, what is it? You said it was exothermic. Have a smell. Good job. I think that's what I mostly heard. Any questions on why? There. Okay, so we just did this method for calculating delta H from bond energy. So that's what that means, is finding delta H from bond energies is using bonds broken minus bonds broken. All right, let's move on to our next method here, which is using this thing known as a delta H of formation. So a delta H of formation is another thing scientists have calculated, and there are a massive amount of data tables of. And it's similar to the bond energy, but also different in what it represents. So if you want to, I would highlight here this little F. That's right there with it, or like in the equation, right? Like the key thing here is that little F indicates that you're looking at what is known as the enthalpy of formation. What do you visualize when I say the word formation? Or forming something? Say louder.
Bonds.
Right, it's like the coming together of creating a molecule. What the enthalpy of formation is it's the energy it takes to create a substance from its elements only. So a lot of times, actually in actual life examples, when we create a chemical or a compound, we don't actually make it from its individual elements. We take it, other compounds, react them, and then they make the compound I want. A great example is glucose. How is glucose often made every day? Anyone? Oh, I heard someone say really quiet. There it is. Thanks, Evan. Have a smiley face. It's in photosynthesis, right? Do you remember the equation for photosynthesis, Evan? If you don't, I don't blame you. Do you remember the basic pieces of what makes up photosynthesis? So that's what glucose is, right? So glucose is C6H12O6. What do plants need? Sunlight, water, and oxygen, right? So this is typically created from CO2 and oxygen and sunlight. The formation equation is actually not that, and it's actually like, I don't know if anyone would ever make glucose this way, in like real life because it's like way more difficult than in photosynthesis. But what we mean by formation would be making it from its actual individual elements. So this is the formation equation for glucose. And then scientists have determined what is the value of that equation, like how much heat did it take when this was formed. By using that, we can then use an equation where we take the value of the products minus the reactants. This one is on your formula sheet, by the way. Once again, the weirdness of why they pick and choose, I have no idea. Okay, all right, let's try a problem. Once again, context clue of how I know I use this equation is they're going to give me delta HFs. So recognize, you're going to circle this box. Remember, the way I know I'm using this equation is because they gave me the formations. If you don't have the formations, that equation is pointless. All right, so the equation is we want to do products minus reactants. I'm going to use two different colors for our products and reactants again. All right, so keep in mind the equation is products minus reactants. All right, so on my product side, I have 6 CO2s. So I'm going to do 6 times negative 393.5. And then plus 3 of my waters, which is negative 241.9. Stop me if you don't understand where something came from. It shouldn't feel magical, it should feel logical. And then reactants, I have 1 C6H6, so that is 82.9. And then I have 1 oxygen, which isn't on my table. What? Anyone know why? It's not there. It wasn't a mistake by Miss Alviso, so sometimes it's the answer. Bryson, what do you think? Brian?
Does it not, like, absorb or give up?
It is 0, so the value is 0. Do you know, can you expand on why maybe that is?
I have no idea.
Okay, how's my face? Thanks for trying. Anyone know why would the formation of oxygen be 0, Levi?
I think if you're not breaking any bonds, or not.
You're on the right track. Do you want to add to it?
Oxygen is a diatomic particle, so if you want to make it from scratch elements, you make it from alkyl.
It's just there. It's just an element, right? Pure elements have a delta HF of 0 because you don't form elements. They're just here, right? So that will keep that in mind. If something is a pure element, its delta HF will always equal 0. Daniel, if I have a smiley face if I didn't say that. Does that make sense why, right? Because you don't form an element, right? I can't say, hey, go form some calcium in the lab. Technically through nuclear means, we can form chemicals. But nuclear chemistry is very different from the chemistry we're talking about right now. So, okay, let your calculator do the work. I got an answer of negative 3169.6. And then we're just at 3169.6. Questions on this method? Yeah, Ian.
Do we have to memorize those numbers?
No, those would be given to you every time. Yep, so. It's kind of another hint of like, oh, I know what equation I'm gonna use because they gave me this chart. I'll be honest, the AP test doesn't give very much unneeded data. Like, they don't just throw random things at you just to like confuse you. So if it's there, you're probably gonna use it. Good question. Any other questions before we look at our final method? Okay, so bond energies was drawing the Lewis structures, bonds broken minus bonds formed. Delta HF is this method of products minus reactants. And then our last one we're going to learn is from an equation. Before we do that really quick, everybody, it looks like you need a stretch break. Stand up for me. This is one of my new goals, is to try to give you at least one stretch break every day. So if I forget, someone let me know. Okay, but while we're standing, we're still going to use our time productively. With you and your table buddy, let's see what we did. Did I do that one already? Okay, with your table buddy, whichever one of you is closer to the front of the classroom, between the two of you, you are going to give your partner a quick 90-second recap of how we just solved this problem. Ready, set, teach.
Numbers.
Okay, have a seat. Okay. Okay, so the last way to calculate delta H is by using chemical equations in recognizing them as heat is an additive process, and so if it takes multiple steps to get to the end product, and I know the energy it needs for each step, then we can just add up the step's heat to find the overall enthalpy change. It's known as Hess's law. That's the person who kind of derived it. Doesn't really matter if you know it by name, but that's what I mentioned. I say, oh, we're going to use Hess's law. Hess's law is the idea of rearranging equations to use the steps to get to the end goal. Okay? Now, with rearranging equations, we do have some rules we need to consider. Okay? The rules that we need to consider are, number one, enthalpy is an extensive property. What that means is it's dependent upon the amount we have. Simple example is, if I have more wood, I'm going to have a bigger fire. And so if you increase the amount, you need to increase the heat by the same factor. So if the equation doubles, the heat will double because it's an extensive property. The opposite of an extensive property is an intensive property or an intrinsic property. Can anyone think of a property that doesn't change even if you change the amount of your substance? Like whether I have 10 grams or 100 grams, this property doesn't actually change. Yeah, Zach?
The molar mass.
Perfect, yep, molar mass doesn't change depending on how much you have. Good, have a smiley face. Anyone have another example? Something that doesn't change even if you have different amounts? Yeah.
The rate of the reaction.
Ooh. The rate can change, but you can say the rate law stays consistent. The actual value of the rate, though, because remember, if you have like more of something, it can make it go faster. But the rate law should stay constant all the time. Yeah, that's a good one, Brian. That's my piece back. Dylan?
The molarity.
Yeah, molarity, right? Whether I have a teaspoon of my HCl or a big beaker, they can still both be 5 molar solution. Could have a smiley face. Jack?
Specific heat?
Yeah, specific heat is a great one. Yep, doesn't matter how much water I have, the specific heat is still 4.1. Good, Jack. Have a smiley face. Okay, but keep in mind, heat isn't that way. It does change by amounts. Okay, rule number 2, so that's rule number 1, is if I increase amount, I'm going to increase my heat. Rule number 2 is that if you flip an equation, and I'm going to do it in reverse, the magnitude stays the same, but the sign changes, right? So if a reaction as written takes 890 kilojoules, if I do it in reverse, now it's going to take negative 890 kilojoules. So the sign flips if you flip the equation around. Okay? And then finally, the states of the products and the reactants do matter because the heat of water as a gas is different than heat of liquid water. So just kind of paying attention to those small subscripts can make a difference. Okay? All right. Before we do our problem here, I have a quick question to ask. Okay? This is my house. Okay? And today I need to get to Costco. I know that from my house to Smith's, okay, is 2 miles. Okay? And I know that from Costco to Smith's is another 2 miles, but I don't know how far it is from my house to Costco. Anyone help me? Lily?
Well, if you go from your house to Smith's and then to Costco, that's 4 miles.
Why?
Because you go, if you add the 2 miles from your house to Smith's,
Uh-huh.
and then you add 2 miles for Smith's to Costco. So
It's
assuming they're in a
Costco,
straight
right?
line.
Yeah, it's a straight line, by the way. It's on Redwood Road.
Well, then it's 4 miles.
Yeah.
Why don't you just use Google Maps?
Asking you guys is way more fun. Okay, did everyone understand that that's 4 miles? I know you're always gonna be like, Ms. Amazing, you've got crazy. This is Hess's law. The idea is we have some steps. Right now the steps aren't in order, technically, right? Because this is house to Smith, Costco to Smith. In a sense, we need to flip the second equation around, but the number is staying the same to get the steps in order. So that's what we're going to do in a second is I'm going to show you a chemical equation. I'm going to have an end goal. The end goal was I want to get here to here. We need to line up the steps so they get us there. Okay? All right, thank you, Lily, for playing along. Have a smiley face. Okay, so here's our question. These are our steps. Okay, so they give us this step 1, here's the heat. Step 2, here's the heat. This is the goal. The way you can get, I guess the best way, maybe this can be applied to all life, but with Hess's law, focus on the goal. If you focus on the steps, it can get very confusing. Okay, focus on the goal and keep your eyes on the goal and everything will take care of itself. Okay? Now, the things we need to look for is we need to make sure our steps turn into our goal, that we actually get to Costco and I don't just go to Smith's and then I go back home again because I don't know how to go from there. Okay? So the first thing you're always going to check with Hess's law is location. I'm going to use different colored markers again here in a second very strategically, and I'd encourage you to use them the same. What I mean by location is we need the reactants of our goal. Okay, so if it's a reactant down here, then it needs to be a reactant in a step. So let's start with number 1 and then we'll go to number 2 in a second. Okay? So, coming to my goal, I need solid carbon to be a reactant. Looking at my 2 steps, 1 and 2, we need to find carbon and see if it's a reactant, and if not, fix it. Which equation has just pure carbon? Just 1, right? And look, it's a reactant because it's on the left side of the arrow. Keeping arrows lined up here will help a lot, by the way, as we write them. Okay? So I don't want to change number 1. because I need C to be a reactant. So what I'm going to do off to the side here is if I've decided it needs to stay the way it is, I'm going to rewrite it to keep it that way. So I'm going to just write it over here as C plus O2 turning in to CO2. Now, just to emphasize, because a few students were getting confused by this last period, right? C by itself is not the same as CO2, right? When things are in a compound, they're no longer their identity anymore. This is graphite or coal or diamond, depending on the form. This is what we breathe in. Very different things, right? Okay, so check on the first one. All right, changing colors. Let's go to O2. All right, do I want O2 to be a reactant or a product? Right, the arrow's here, so I want it to be a reactant, okay? So I want it to be on the left. In equation 1, it is on the left, which is good because we don't want to change equation 1's order. Now, technically, in equation 2, it's also on the left. Being that it's in both equations, that actually gives me some flexibility of whether this has to stay or not. I know this is going to stay because I'm not ever changing this one. So we're going to leave that there and go to our last piece. So third color here. So CO, I want to be on the right side and a product. Which step or which equation gives me CO? So equation 2, this is the only time, so I underline once again matching CO, but it's backwards.
Oh no.
So I'm going to rewrite my equation and flip it. So it's on the same side as my goal. Okay, so coming over here, I'm taking this equation 2, and I'm going to write it in reverse. So we have CO2, keep the arrow lined up, CO plus 0.5 O2. Now the difference between distance and heat energy, right? So Lily said like if it takes 2 miles to go from Smith's to Costco, or Costco to Smith's, it's going to take 2 miles to go the other way. In heat, what's going to change though? The sign. So we need to flip that sign to positive. Okay, so positive sign because we flipped the equation. Okay, so we did step 1, we checked the location of the goal and matched it up with our equation. Step number 2 is you check the amounts. Do the amounts match in the equation as they do to your steps? Okay? Now, what's happening here, it's going to have a similar feel to mechanisms. We're going to bring the steps together. So when we did mechanisms last unit, what happened when something appeared on both sides of the arrow? Good, they can cancel out. Now, there has to be the exact same amount. So this has 1 O2. This has 0.5 O2, so it doesn't cancel perfectly. How much left over would I still have over here? Yeah, so I'd still have 0.5 O2 left over, because that canceled out with, in a sense, half of those. So that was still left over. The carbon, there's nothing to cancel out with, which is good because I didn't want it to cancel, so I'm going to carry that down. Okay. CO2 is also on the left, but it cancels perfectly, so CO2 cancels away. Okay, so I'll make a note that we're cancel out if same on opposite sides of arrow. So then on the product side, the only thing that hasn't canceled out is CO. our goal? That. Does it match?
Yeah.
So then if it matches, now we can just add up the heats. Woo! So we add up negative 293.5 plus, this is now positive, right? 283.0. And so the heat change for this reaction is negative 110.5. So we had the steps, they just weren't in the right order. So we had to rearrange it to get it how we needed. Questions on what we did before I have you try one with your table buddy? Okay, now, we didn't do it because it didn't apply to this one, but let me just hint that maybe on the next one we might have to do step 2. So what I mean by amounts is, let's say hypothetically, everyone give me your eyes this way really quick. Let's say hypothetically the goal reaction said you needed 2 of those. Okay? What that would mean is, in order to get a 2 here, because when I add them together it's not giving me 2 of those, right? I would need to multiply this whole reaction by 2 and multiply that by 2. Now, it doesn't work for this problem because it doesn't need it. But I'm saying if you see that there's like, oh, there's 2 of these here, and the equations as written don't give you that, that's what we mean by amounts. Okay? Alright, I'm going to give you 5 minutes to try out the practice problem right below. Once you think you've gotten it, raise your hand and I'll come check it off or help you out. Okay? Ready, set, go.
So minus 50.
I would encourage you to communicate with your partner as you work with them, right? It'll help your understanding. Once again, focus on the goal. I focus on location first, and then amount. Focus on the goal, take it one piece at a time, and then it will work itself out.
Oh, I get, okay, yeah.
Focus on it.
And then H.
Pretty much all we did was switch it around.
So the end thing is you're always going to add, but you have to make sure everything's in its right place before you add.
So this one, we're gonna have to start around and multiply this one.
Cancel H2O, cancel out 1 CO2.
Add all these up.
Yeah, once everything's in its right spot, meaning flipped or doubled, then you should just go add them.
Technically, if I want to I can just do that plus it.
It's not theoretical.
Yeah.
Because then I can tell you you're right or not if you have everything correct. But yes, your logic is sound though. Should I just drop it?
I mean, you guys sound right. Oh, yeah, and then it would just cancel out. So it would just CO2. So you cancel all the CO2. Cancel all that. Cancel out.
Once you have an answer, let me know.
Okay, so let's just.
Yes. Help your partner now.
Oh, wait,
Good.
and the 0.502 would cancel out, so there's no
There you go. You are on the right track. You got the most common wrong. So you done? One, two, first we get them into position when right now it's written, things are not counting position, right? Think of we need to make it feel ready so that we put them around so that it works out to the best.
Oh, I know what I did wrong.
So part of it needs to be which equation
I just thought one was, I just one
that one you go
I was like, wait, this is not actually.
So these ones we don't want to pass. We want C2H9.
That's what I was talking to her about.
There you go. Equation 1 needs to, or maybe rewrite equation 1 down below or something.
I am right.
And maybe you are. That's it.
But I was like, so pretty much all I have to do is
Almost. You did it here, but you didn't do it there. So, you times this whole equation by 2. What's that going to do to it?
Oh, it's times.
You did it in the equation, you just didn't do it for me. So fix that and then you should be fine.
Okay.
Nice.
Minus 393.
Well done, have a smiley face. Good
226.
job, have a smiley face.
I bet you're glad you might have
Good job, have a smiley
we're
face.
checking your calculator.
Good. Check with Caleb when he's done so he knows. Did I see another parent that's weird? Good job, guys.
Yeah.
All the same. United table. Good job.
Why did I do that? I was too busy doing my
Okay, I checked most. Is there anyone I didn't check that? Check still. If you need another minute to finish up, that's fine. I guess I'll just say this. So, that's it for today. We finished our lesson, which is amazing because we got 6 minutes to work on homework. Woo! So, pull out your homework because we don't clean up until there's 1 minute left, not 6. Okay, so if you want to do another problem like this one where it's fresh on your mind, that's the back side of 6869. So you want to go straight there, or if you want to go to 65, however you want to do it. And if you haven't solved this or checked it off with me, let me know and I'll check it for you, okay?
And the questions were the same too.